This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
Welcome to the fourth lecture of the Winter School. We're now considering differentiable manifolds, and so far we looked at topological manifolds. And a topological manifold, roughly speaking, allowed, due to the topology on it anyway, the definition of continuity of a curve. And if you think of space and you think of this curve as the trajectory of a particle, in classical physics you certainly want to talk about continuity, and you want to require that this curve doesn't make jumps. We already achieved that. Now, roughly speaking, you want also to associate to this curve at every point a velocity. That's the basic idea. Now, it's pretty clear that if the curve looks somewhat like this, then you have difficulty associating a velocity here because there's no unique tangent vector, very roughly speaking. Okay? The question is, what's the difference between this curve and this one? Well, roughly speaking, intuitively you say this one is a differentiable curve and this is not differentiable. Huh? But now we need to make this precise, and the question is the structure of a topological manifold MO, so we already assume it's a special topological space, namely a topological manifold of dimension D. The question is the structure MO enough to talk about differentiability of curves? And the answer will be a resounding no. It's not enough. Can you construct from it a notion of differentiability? No, of course not. That's what I mean. It's not good enough, not enough information. You need to make more choices before you can actually talk about differentiability of a curve. And in this lecture, we'll figure out what the amount of this choice is and how much choice you really have. I tell you already now, in dimension 1, 2, and 3, you have choice, but they're all equivalent, so you have only one choice. In 1 to 3, it's pretty clear. I mean, 1 to 3 dimensional topological manifolds, you have essentially one choice how to talk about differentiability of curves on them. 1, 2, 3. Dimension 5, 6, 7, 8, 9, 10, and so on. So not 4, 5, 6, but 5, 6, 7, 8. You have in each dimension a finite amount of choice. Okay, so you say, well, you have 48 choices. Well, write it down, do physics with it, make experiments, and you will find out which of the one it is. Unfortunately, there's a theorem, which I will quote in the end, that in 4 dimensions, the dimension of space-time, you have an uncountable number of possible choices. Do you still think it's obvious which one to choose? It is not. It's important to figure out what is going on. Okay, so this lecture is about figuring out what structure we need to add on a topological manifold in order to start talking about differentiability of curves on a manifold, about differentiability of functions on a manifold, even about differentiability of maps from one manifold to another manifold. We will need all this. Okay, so we wish to define a notion of differentiable objects, more concretely curves. What was a curve? Well, on a manifold, a curve is a map from R to M of differentiable functions. That's just the terminology for a map from the manifold into the real number, say a temperature distribution on the manifold, and most generally maps from one manifold to another. So I will now not always specify that there is a topology on here because I say it's a topological manifold. You know that is in the background, has been chosen. We want to define such a notion. Now, first, what is our strategy for that? And in the second lecture, I already indicated what the strategy would be. I spell it out once more. The strategy is, if this didn't happen, if we didn't look at a curve in the manifold, let's start with curves. So if we didn't look at this guy in the manifold, but we rather looked at a curve from R to RD, we would know what we mean by differentiability, right? And we could use the undergraduate definition and talk about that. Now the point here is the strategy is choose a chart UX. Well, a chart will not cover the entire manifold, but let's start in a chart and consider the portion of the curve that lies in the chart domain. You can say, well, that's not what we want. We don't want the portions that lie in a chart domain. We want the full curve. But let's do it in charts, and because chart domains cover everything, we can then compose the global notion from the local notion. That's the strategy. We try this and we'll see how it works. Okay, but now how can we do this? Well, if we have a chart, we also have a chart map. We land in x of u in RD, and here of course we got, already last time, the object x after gamma, which is now a curve from R into RD. But as a curve from R to RD, we know whether it's differentiable or not. You take the derivative with respect to the curve parameter component-wise, or something like this. Okay, your favorite definition here. And the strategy or the idea is try, I think the chalk is wet here, try to lift the undergraduate notion of differentiability of a curve on RD to a notion of differentiability of a curve on the manifold. Right? We already had the question last time, well, here you call it differentiability, and then you used to call this also differentiable, but this should be called undergraduate differentiability, and this is called the manifold differentiability, okay? But you try to define this by coming from here. Now, of course, already the problem, or the question we encountered last time is, can this be well defined? Can this be well defined? Because after all, the curve doesn't know anything about me looking at a particular chart. It would be a very bad idea to assign the curve a property that depends on my taste. So well defined, is this well defined under change of chart? So in order to judge that, we again draw this picture. Gamma, the portion of the curve that lies in u. You use one chart, you go to x of u in RD, but now another chart could have another chart domain, and it could have another chart map, both at the same time. Now if the other chart domain is V, and the intersection between the two is empty, then one chart here, one chart there, they can't be incompatible because this portion of the curve has nothing to do with that portion of the curve. But if this is non-empty, then in the overlap region there is a real problem, because one chart map might tell you, yes, it is differentiable down there, of the same curve, of the same object in the real world. The other chart map might tell you, no, it isn't. Well, if that happens, that's catastrophe, because then our definition is no good. So that means we look only at the non-empty overlap region, but then because this is U is part of the overlap, you can of course still use the x to map here. This will still lie in RD, and on this part you have x after gamma. Now another chart on this entire overlap region using y gives you y of u intersected v in RD, and you have another chart map y after gamma. And now the question is, if I use here, if I say this is undergraduate differentiable, and of course that's just my term for as a map from R to RD. This is what I mean by undergraduate differentiable. If this is undergraduate differentiable, question, will this representative of the same curve in the real world be undergraduate differentiable in the other chart? Well, we know we have a chart transition function here, y after x inverse from here to there. That was exactly the chart transition function. And let's write it down. So that's this guy, y after gamma is of course y after, what do we do? Y after x inverse after x after gamma. You can read it this way. This is this one after this one. But of course the composition is associative, so you could write y after x inverse after x after gamma. You can think of it this way. Then you see, oh, it's really this guy here by inserting the identity. Whatever way you think about it, this is all true. But the point here is this guy here, you know, is undergraduate differentiable, undergrad diffable. And in fact, it's really a map from R to RD. This guy is a map from RD to RD, right? From some portion of RD to some portion of RD. And you know, however, because it's a chart in a topological manifold, two charts in a topological manifold, what you know with certainty is that it's continuous. Well, you could also call it undergraduate continuous because it's continuous with respect to the standard topology in RD. But now you see the problem. The composition of a differentiable map and a continuous map may be differentiable, but it may not be. All you can conclude is that the composition here is sometimes, maybe, only continuous, not undergrad differentiable. Roughly speaking, because a continuous chart transition map can make an edge like this, right? And it destroys the differentiability. So the answer is, it doesn't work. It simply, this does not work. Now, what is the remedy of the whole thing? By the way, if you now want to study this, the diagram looks very similar, and a similar problem occurs. If you wanted to define the function on a certain domain, you try to study how it looks as a chart representative of the function and so on. And here, for these maps, the diagram looks on both sides. You have to choose charts here and there, and the diagram becomes bigger. But it's always the same problem. If you change chart, and you only know that the chart transition map is continuous, as is guaranteed by the topological manifold definition, then you're in trouble. Your strategy does not work out. So at first sight, strategy does not work out. But of course there is a remedy for the whole thing, and that's section 2, compatible charts. So let's make a bit more explicit what we said before. In section 1, we used any imaginable charts on the topological manifold MO. And in order to emphasize, I mean, of course, a chart is a chart. In order to emphasize that we took any charts possible, we say the following: to emphasize this, we may say that we took U and V, these arbitrary charts, from the maximal atlas A of MO. Again, an atlas was just a collection of all charts. No, sorry, an atlas was a collection of enough charts such that the chart regions overlap the entire manifold. That's an atlas. The maximal atlas is an atlas that has many more redundant pages. Namely, any page you could put in is in there. So the maximal atlas is a theoretical object. I would never, if I want to give you an atlas, I would always write down a minimal or an almost minimal atlas, at least a small atlas, as small as possible somehow because it saves work. But then I can imagine, you can ask, does an additional chart lie in the maximal atlas? Okay, and the answer is if it's a chart, it lies in the maximal atlas. Okay, so this is the, and so we say we took U and V from the maximal atlas. But some of these guys, we might be lucky, maybe this maximal atlas can be reduced such that I throw out all those charts which have between them a transition map, a chart transition map that is only continuous but not differentiable. Because the chart transition map is also from RD to RD, we can use our undergraduate understanding of differentiability and require that we only keep a subset of charts that we originally had in the maximal atlas, and we pick in a clever way such a subset that it's still an atlas, it still covers, but that all transition functions are differentiable. If we manage to do that, we make this work by additionally requiring that in the future you cannot just choose any charts in order to define this, in order to define the differentiability of this curve. You may only define the differentiability of the curve from the chosen charts, from a restricted atlas. But if you do this, everything is fine. Okay? So, definition. Let's make this formal, this idea. Definition. Two charts, Ux and Vy, of a topological manifold. So first of all, of course, it's any charts, are called flower compatible if either, two possibilities, if either their chart domains do not overlap at all. Somebody you don't meet, you can't be incompatible with, right? You never got into trouble with. You're compatible with everyone you didn't meet. Charts who have no common part of their domains, they are compatible. But now, what if there is overlap? So either or. If there's overlap, they're called compatible if either the chart transition map between them, now chart transition maps, we've got to be very careful, there are two. If you have two charts, you can do y after x inverse, was the one we wrote there, y after x inverse. Now what's its domain? Its domain is the image of the intersection, and its target is the image of the intersection under the other chart map. So that map is over there. If the transition map's this one and its inverse, that's this one, x after y inverse, there the domain is y of u intersected v goes to x u intersected v. Of course, one is the inverse of the other. One could maybe not write this and say, well, you could rename u in v and x in y and then it's contained, but it's clear like this. If in both directions these maps, these chart transition maps are, and now comes the point, because they're both maps from RD to RD, right? Both maps from RD to RD. I can use any notion of undergraduate flower property in order to define flower compatibility on the manifold. For instance, if I have a notion of undergraduate on RD differentiability, I call two charts differentially compatible if the chart transition maps are undergraduate differentiably compatible if they're differentiable, if they have the differentiability property. Okay, so why do I use the ridiculous flower? The point is, this is the philosophy that you can have different types of manifolds and different types of compatibilities. You define an atlas A flower is a flower compatible atlas if any two charts in a flower are flower compatible. And then you say a flower manifold is a triple MO A flower. And of course the A flower must always be a subset of the maximal atlas because it's an atlas. Okay, it still covers. And that's a flower manifold, is a triple where of course these two entries make a topological manifold. But you have to choose a selection of charts that are mutually flower compatible, whatever flower is, for instance, differentiability. Okay? And that's a choice. And it's not clear for a given topological manifold, say the sphere, and I have the maximal topological atlas, can't I take out charts in one way, or can't I keep one set of charts or another set of charts that both satisfy the flower compatibility, but the choices are not the same? If that happens, and I wish to make a model of space-time, I should know which choice I make, because one is not the same as the other. Under one choice, some curves will be differentiable, for instance, and other curves won't. So I need to know. And the question of how many choices I can make is very important in order to know whether I introduce arbitrary assumptions here or whether this is the only way I can do at this level. Right? So this is, for physics, this is important. This is not mathematical sophistication for its own sake. This is a really down-to-earth question for physics. Am I choosing the right structure here? Now, I said it's the philosophy. Let me make a table of what flower can be. Yes?
May I ask a question for that? Why do we require that the overlap between U and V can also include the zero overlap in the definition of flower compatibility?
No, you mean this one here? Well, the zero overlap means it has no overlap. So it would be the real world. And there's one chart domain U here and one chart domain V here. They map this part of the world and this part of the world. They can never cause an incompatibility in the definition, because there is no portion of a curve. Say there's a curve in the world which maybe even hits both domains, but then one can only judge the differentiability here, the other one can only judge the differentiability here, but they can never be in conflict. Hence, if charts have non-overlapping domain, if the intersection is empty, we don't have to worry, they are compatible. But if they intersect, then you can judge the same piece of the curve in one chart or the other, and then you may have a problem, and there is where the condition needs to be imposed. That's it. Okay, so what can flower be? This is flower, and this is undergraduate flower. And of course, this is silly, but one thing we like to write sometimes is C0. Are these C0 compatible atlases? What it means are the transition maps C0 as maps from RD to RD. C0 means is the set of all continuous maps with respect to the standard topology on RD. And you say every atlas is a C0 atlas on a topological manifold because the transition maps are of course continuous. So every atlas is a C0 atlas. Now you can ask, is the atlas C1? What is C1? C1 would be this. What is undergraduate C1? Well, it would be that the transition maps as maps from here to here. I mean, strictly speaking, from where they are defined to where they're defined, right? Roughly speaking, with respect to O standard, these are the maps from R to D to RD that are differentiable, namely once, and the result is continuous. You could have a function that's differentiable, but the result is not continuous. Okay? That's this. Of course, you can generalize this to CK is the function k times continuously differentiable. Now you ask, why do we insist on the result being continuous? Well, you don't have to. You could ask, is it k times differentiable? But the nice thing about functions that are not only k times differentiable, but the result is continuous, is that you can judge its k times continuous differentiability from the repeated continuous differentiability in various directions. So from the existence of the partial derivatives and their continuity, you can already conclude the entire map has this property, because there are nice examples that maps are differentiable k times. There are examples for maps that are not k times differentiable as maps from RD to RD, but all partial derivatives are, right? There are examples like this. But because it's nicer to not have to worry about these cases, you require the function itself to be continuously differentiable. Hence, this is a more favored class of manifolds than those. They're easier to work with. Okay? But anyway, so you have this. Then there is a class that's called C infinity. C infinity compatibility means you can, it's continuously differentiable arbitrarily many times. Okay, that's C infinity. Then there is a case that's called C omega. Omega stands for analytic, real analytic in this case. That means this transition map can be Taylor expanded, right? A multi-dimensional Taylor expansion. So there exists a multi-dimensional Taylor expansion, right? So in physics, sometimes people say, well, everything can be Taylor expanded. No, right? It's simply not true, right? It's much stronger than this one. Right? This is a much smaller class than this one. Okay. And finally, maybe I don't know how to call this, complex differentiable or something like this. Yeah. This you can do only for even dimensional manifolds, and you can require that your chart map, which is from R2D to R2D, that they pairwise satisfy the Cauchy-Riemann equations. If you do that on top, then you get something called a complex manifold, which has much more structure than a real manifold, because you additionally have the Cauchy. But you always ask this of the transition functions. So by imposing more and more conditions on the transition functions, and why would you do that? Well, because you might want to define a Taylor expandable curve. But then you need an analytic manifold in order to not destroy the Taylor expandability in one chart once you transit to another one. So the more fancy stuff you want of your objects on the manifold, the more restrictive you have to be in your choice of atlas. And the question is, yes?
The C omega, whether I have just a two-dimensional Taylor expansion or a 100th dimensional, that doesn't matter, it's all C omega.
No, it would depend on the dimension. So the question was whether whether it matters whether you have a analytic function in one dimension or in two dimensions. Well, they're totally different functions, okay? And so you can't even compare. You can't even compare. But it's certainly not, if it's smooth, this is called smooth. There are smooth functions that are not analytic in any dimension, right? Okay, so this is the general philosophy. So in the future, if you hear of a complex manifold, you say, ha, it's just here the Cauchy-Riemann equations apply to the transition maps. You know what a complex manifold is, okay? So this is the general overview here. So that's what we want. And I think it's clear now from what I said in the beginning, I don't need to say it again. Now our definition of differentiability of a curve, say our curve can be called k times, the curve on the manifold can be called k times continuously differentiable on a manifold where I manage to find an atlas that is a CK atlas, because that will preserve this property in one chart for another chart. Okay? Now the question of course is, okay, to what degree do derivatives appear in physics? Okay, is C2 enough? Maybe C3 to be safe or whatnot. There is actually a nice theorem by Whitney that says we don't need to worry about this. Theorem. Without proof. Any CK manifold, so remember, that's a manifold, it's a topological manifold on which there exists an atlas that is CK, but K needs to be bigger or equal, greater or equal than 1. So it's not for a C0 manifold, of course, right? Any CK, so if you have a manifold for which there exists an atlas, where you can reduce the atlas such that all the charts that remain and still constitute an atlas are at least once continuously differentiable, the transition maps. Any such manifold, I should formulate in terms of atlases, and then it's shorter and clearer. Any CK greater than or equal 1 atlas, A, CK greater than or equal 1 is its name, of a topological manifold contains, as a subatlas, which is still an atlas, contains a C infinity atlas. Meaning, if you have a topological manifold, there are some topological manifolds where you simply cannot remove a chart or charts in such a way that all that remains is still an atlas and has continuously differentiable transition functions. So some topological manifolds cannot be given such a structure. But those who can, where I can achieve that the transition functions are at least once continuously differentiable, and I have an atlas, in that atlas you can remove more and more and more and more charts, this theorem says, until you have even a C infinity atlas. So the difficult step is from a C0 atlas to C1. That step is really substantial. right? This might or might not work to choose such an atlas for a given topological manifold. But once you arrived here, you trickle down right up to here. Meaning, in the future, I will do hell and specify which CK. I will always use smooth manifolds. Thus, we may, without loss of generality, OBDR, we may, without loss of generality, always consider C infinity manifolds, and they have a name, they're called smooth manifolds, because that's nicer, that's smoother than saying C infinity manifold. Smooth manifolds, unless we wish to define Taylor expandability, complex differentiability, and so on, because it doesn't trickle down to here, okay? But we don't need this. Although as physicists, sometimes we may want to like this, but then you really have to make sure that your manifold, your underlying topological manifold, still allows you to further reduce the atlas. So you see, as a physicist, you cannot say, ah, come on, let's Taylor expand a little, right? Just a little, right? Okay, good, good. So, well, it's already said, but maybe once, a smooth manifold is a triple MOA, where this is a C infinity atlas, and this is a topological manifold. And you see, the only thing that distinguishes a smooth manifold from a topological manifold is the provision of extra structure. But in this case, it's not extra because I put it on top, right? But because I reduced it from a given atlas, but ripping out pages, page 7, page 28, page 510, also contains information. Because I could have ripped out the pages, I could have ripped out other pages, and I send a message, I love you, or I don't quite love you, right? So this is information choosing this atlas.
Just because for me, manifold is something like physics. This was always from RT to RT. This means this is a chart transition map.
It's a chart transition map.
Where does then the gamma has to come from the experiment? If gamma is really C infinite.
Sorry, gamma, what's gamma? The curve.
The curve, yeah.
No, the curves, again, so the question, yeah, okay, so the curve, the setup is the following. So I throw this piece of chalk, sorry, okay? Now, it made a trajectory, okay? And I like, as a physicist, I think of the trajectory that this piece of chalk made in the real world. And I might, with sufficient idealization, say, if this is the real world, then what the chalk did, and I may think of this as time, which later on we won't, but roughly speaking, this is the curve that the real object in the real world made. And then, of course, in order to communicate to you, because you just didn't look there but looked out of the window, what did the piece of chalk do? I set up a chart, I put up little flags everywhere and so on, and you will say it passed my nose right here, and you say it passed my nose at that and that time, and so on. So I set up a chart, and then I give you this here. I can write it down on paper, maybe even as a nice function. I tell you this. And of course, once I set up a chart this way, I can write it down this way. But as a physicist, what the trajectory of the chalk is not this, the trajectory of the chalk is that. Now, of course, if we write down physics on paper, I mean concrete curves, we'll always talk, or almost always talk, about this guy, and you may change chart, and then you talk about this guy, and so on. But what we really think about, and the things really one should attach properties to, or require properties of in our model of the world, is this guy, what the real path of the real chalk. And all this reminds you is you may have a fantasy of saying, well, but it was differentiable, the curve I wrote down to you. Well, only because we made very special provisions of not choosing charts here that don't allow to speak of that. Yes?
Let's assume I have a hammer and I knock onto a ball. Yeah?
Okay.
And this is a delta pulse, and it is in the third or fourth or fifth derivative discontinuous.
Okay.
How does this, I don't see
Okay.
how this works.
Okay. Yes, yes, yes. Well, the point would be if I say you have a smooth curve. So the question was, I'm sorry. So the question was, what if you have a pulse with a hammer? You hammer on something and the fifth derivative is discontinuous. So the head of the nail makes it discontinuous. Well, it makes well. So, yeah. Well, the point is, if you say world lines or trajectories are smooth, you would not allow that. Now you can say I have a smooth manifold, but on a smooth manifold I can define a C2 curve, right? So if I say I want this to be C2, so that if you derive once more 3 times as you required, it's discontinuous. That means you don't require the curve as C infinity, you only require it C2. Nevertheless, you can still do this on a smooth manifold with these transition functions because C infinity after C2 will generically only be C2. Right? So it doesn't harm that you choose a C infinity manifold if you still want to consider, for whatever reason, curves that are only C2 but not C3. And all the Whitney theorem says, it doesn't say the objects you look at must then be C infinity. It says it doesn't harm the C2 objects if you choose the manifold C infinity, and you always can. Okay? So therefore, it's a good question, because I maybe overstated before. I said we can always choose our objects to be smooth. We can still insist on them not being smooth, but for the chart transition maps, I still require smoothness, and everything will be well defined. Okay? Okay. Where are we? Diffeomorphisms and the theorem I mentioned in the beginning. So, last section, diffeomorphisms. So I already mentioned that whenever you have maps from one set to another set, and it's just some map, let's call it capital Phi, if you have no further structure to the set, you can say you can study sets by studying maps between them, and that's just maps. They have no further structure, and what you usually require is that the map is invertible. So if you on a naked set, so if Mn are naked sets, meaning you have no further structure in mind, the structure preserving maps, so not only respecting but preserving maps, are the bijections. And those are, of course, the invertible maps, for which there exists an inverse. Because at a set theoretical level, a set, roughly speaking, consists of its elements. And if each element here, you can map to one here, everything is hit, and none is hit twice, you can pair. Girls with boys, and you know, you can pair this up. And so two sets may be such that they do have, that there exists such a structure preserving map or not. So example, between the set 1, 2, 3 and the set AB, there exists no structure preserving map at the pure set level, because I can map the 1 to the A and the 2 to the B, but what do I do with the 3? I would have to map it to A or B again, but then it wouldn't be bijective because no inverse exists. And in fact, you compare the size of sets, informally speaking, by talking about there exists a bijection, then you call the sets to be of the same size. Well, for finite sets, that's maybe a little bit overdone as a definition, but for infinite sets, it works. So for instance, you can, okay, so that's an example where it doesn't work. There exists no structure preserving map. Now, definition, a set M and a set N are called to be isomorphic, and I say set theoretically. So I emphasize only if you look at the set aspects, they are set theoretically isomorphic. Morph is form and iso is the same. They have the same form, set theoretically speaking, only looking at their set theoretic aspects, therefore studying them by maps, by pure maps. They are set theoretically isomorphic by definition if there exists a bijection phi between them. Well, if there exists one, there exists usually many different ones. The question is there at least one one-to-one map? If that is the case, then the one-to-one map is called an isomorphism, but the sets are then called isomorphic. In order to emphasize that this takes nothing into account but the set theoretic structure, we say they're set theoretically isomorphic. And examples are, for instance, the integers are set theoretically isomorphic to the integers to the natural numbers. There are as many integers as the natural numbers. You say, but they're double as many, roughly speaking, apart from the 0. No, but you can make pairs. Okay. A bit more surprising is that the fractions are as many as n, and there's this diagonal counting scheme and so on. Maybe you saw this before. So they're set theoretically isomorphic. But n is not set theoretically isomorphic, for instance, to the reals. Okay, that's this example. Now, that was on the set theoretic level. Now, and that will always stay like this. Now we can add structure to a set. And we did this, if we add structure to the set, we now consider still a set, but equipped with a topology, for instance. We did this in the first lecture. And the question is, can we define a meaningful notion of topological isomorphism? That will still, because there are still sets in there, the topological, two sets will be topologically isomorphic, so topologically isomorphic, but there is a household name for that, and that's called their homeomorphic, and that's just traditional language. It means they are at the set level isomorphic, but additionally there exists not only a bijection phi from M to N, but a bijection such that phi and its inverse are continuous. Why? Well, because continuity is the structure respecting property of these curves. So you add the condition, not only do I want these two there to be a bijection, I want there to be a bijection which in both directions is continuous. If that exists, there may be several of those, then I call the two spaces topologically equivalent. And it's clear, if two spaces are topologically isomorphic or homeomorphic as one says, then of course they're also set theoretically isomorphic. This is a stronger notion. I look at the sets more closely. Okay? So this is here. If you have a vector space, you can do similar stuff. You can call one vector space isomorphic to another one. If again you require there exists a bijection phi between one and the other, if it's a bijection, it means it's invertible, and in both directions it's linear. Because linearity is the structure preserving map here. And finally, I want to show you this is always the same principle. And finally, what I actually want to do in this section is I want to call talk about diffeomorphic maps. So definition, two C infinity manifolds, M, OM, AM, and N, ON, AN are said to be diffeomorphic if there exists a bijection, that's a purely set theoretic thing, bijection phi from M to N, but because there's a bijection, the phi inverse exists such that the map phi and the map phi inverse are both C infinity maps. And I haven't defined C infinity map yet, but it's clear how that goes. If you have an M and an N smooth manifold, you may choose here an open set U, and in the target you may choose an open set V, and you look only at these portions of this map, but here you can choose a chart X and here you can choose a chart Y, and that goes to some RD, but this here goes to some RE, because if this is a D-dimensional manifold where you start and this is an E-dimensional manifold where you land, the charts will have this property, and we would like to call this portion of the map that lands in that portion of that space, we like to call it C infinity if the map Y after phi after X inverse, which now uses a combination of two charts here and there for its definition, if this is undergraduate C infinity from RD to RE. Of course, you know the drill. You need to check whether with alternative charts X twiddle and Y twiddle into RD and RE, you need to check whether the other representation, Y twiddle after phi after X twiddle inverse, whether this is also undergraduate differentiable. But we already know, because we have a chart transition map here and a chart transition map here, which, because we started with C infinity manifolds, you know the chart transition maps are undergraduate C infinity, and this undergraduate C infinity will be preserved if I lift it up to here. The diagram gets bigger and the principle is always the same. Okay? So, why do I bother about diffeomorphisms? Well, if you look at a manifold and you look so closely that it doesn't escape you that it's a C infinity manifold. I mean, certainly it's still a topological manifold, but it's a C infinity manifold. The question is, can you distinguish two C infinity manifolds using only that structure? For instance, if I take a ball, I embed it and nicely and I pull back the topology from R3, right? So I take x squared plus y, m squared plus n squared plus p squared in R3. I induce the topology from R3, the standard topology. I get a topological manifold, we already know, right? Talked about this. And then can I reduce there the maximal atlas such that I get a C infinity manifold? Yes, I promise you can. Okay, so you have a C infinity manifold. Now question, you do the same but with 5 times m squared plus 7 times n squared plus 18 times p squared equals 1, and then you get an ellipsoid. You do the same thing, you pull back your topology, you reduce the atlas and so on. Question, is there a diffeomorphism between this guy and that guy? Yes, there is. Is there a diffeomorphism between the sphere and the sphere where I make a little edge in it, right? I fold it a little. No, there is no diffeomorphism between the two. There is still a homeomorphism between the two. As topological manifolds, they're the same, but as smooth manifolds, they're already not the same anymore. Okay, so it always depends at the level you look at it. But still, the surface of a potato that doesn't have any folds, right? The surface of a potato is diffeomorphic to the surface of the Earth, right? At this level, unless you make a little edge into it, at the smooth manifold level, things don't have a shape yet, apart from not having little folding edges. But a shape they don't have yet. That comes only later. Okay? So now comes this theorem. That's the last thing, theorem. Is on the number of manifolds, of C infinity manifolds, one can make out of a given C0 manifold, in brackets, if any, so for some that might not work, but say you have one for which it works, up to diffeomorphism. So I can equip a topological manifold with two different, okay, fine. I first said up to diffeomorphism. So if two manifolds only differ by diffeomorphism, I count them as one, because through the differential manifold perspective viewed, they are the same. Okay, up to diffeomorphism is the following: dimension of the underlying topological manifold, 1, 2, 3, and the number of different manifolds I can make of that is 1, 1, 1. Wonderful. No ambiguity. 4 I leave open. I said in the beginning 5, 6, 7. Here 5 finitely many, 6 finitely many, 7 finitely many. So this is the Moyes-Radon theorems. So the point is this is not easy to prove, okay? And 5, 6, 7, that they are only finitely many, this has been shown by a field of topology that's called surgery theory, where you have to learn how to glue together manifolds and stuff like this. Surgery theory result, okay? So extra techniques had to be invented in topology in order to prove this, meaning don't worry if you don't feel it, okay? It's a deep result. And now 4 dimensions, which is of course, as space-time physicists we're particularly interested in, there's some partial results that some compact manifolds, compact is a topological notion, okay? The surface of a sphere is compact, but R2 as a manifold is not compact as a topological manifold, right? Anyway, for compact manifolds, there are some where if the Betti number is 18, it's also a topological notion, then there are only finitely many choices, or something like this. Some very, very special exceptions. But generically, and particularly for non-compact manifolds, right, which is a real option for space-time, there exist uncountably many, infinitely many. So not only infinitely many, 1, 2, 3, 4, 5, but so many, like the real numbers, that you can't even count them anymore. Okay? And that's just an existence proof. There exist uncountably infinitely many different C infinity manifolds you can make out of a given topological manifold. So that's a real problem, because which one do you choose for physics? Okay?
For 5 and higher, there are finite number. Is it the same number for all?
No, it isn't.
And how finite? 2 or 3 or 10 to the 10? Or?
Oh, that doesn't matter. I don't know. I don't know whether the proofs actually only say, I only know the statement that there are finitely many. I don't know whether there's any definite number. Probably not, because these could look very funny, right? And some 5-dimensional ones might have 20, and other 5-dimensional ones might have 28 different structures, right? So you can't really say what the finite number is. Okay, I think. I would be very surprised if in dimension 28 the number was 58 for all 20. It could be, I don't know. But finite still sounds fine, okay? For a physicist, you could say, let experiment decide, right? Let's be real physicists, let experiment decide. But if you here want to be a real physicist, you're also a very busy experimental physicist, right? So you see, theory does something here for you. You cannot always say, let experiment decide, right? Okay, thank you very much. See you tomorrow. And in the tutorials, please.